The most widely used method for measuring ozone is based on absorbance of ultraviolet or UV light. As you may know, ozone in the stratosphere absorbs ultraviolet light to protect the Earth from harmful ultraviolet rays coming from the sun. This same property of ozone, the absorbance or blocking of UV light, may be used to measure ozone concentration in the air we breathe. Here we will show how an ozone monitor based on UV absorbance works. To measure ozone in air, we start with the detection cell. This is just a quartz tube that we flow our sample air through. We need an inlet for the air to enter the detection cell and an outlet for the air to exit. Next, we need an air pump to draw the air through the detection cell. This pump works in the same way as an aquarium air pump, except that it uses suction to draw air through the ozone monitor instead of pushing it through. We detect ozone by measuring how much UV light is absorbed or blocked by the ozone molecules. So we need a lamp to output UV light and some kind of light detector. The UV light from a mercury lamp has a wavelength of 254 nanometers, which by coincidence is exactly the wavelength most strongly absorbed by ozone. The simplest light detector is a photodiode, which works like a solar cell. When light strikes a photodiode, an electrical current is produced, and that current can be measured using a current meter. When we turn the lamp on, UV light passes through the detection cell, and the needle on the meter indicates a high value for the light intensity. When we turn the lamp off, the meter reads 0. Let's turn the lamp on again. In an ozone monitor, the lamp is always on, so let's leave it on. Now let's pass some ozone molecules through the detection cell. Notice that the ozone molecules absorb or block some of the light from reaching the photodiode. The light intensity becomes dimmer as the light travels from the lamp to the photodiode. This reduction in light intensity is the basis of the UV absorbance method for measuring ozone concentration. If we stop passing ozone through the detection cell, the light intensity striking the photodiode goes up again and the meter reading increases. From our two light intensity measurements with and without ozone molecules present, we can calculate the ozone concentration based on the Beer-Lambert law for absorbance of light. Here, C sub ozone is the concentration of ozone in units of molecules per cubic centimeter or molecules per cc. Sigma and L are two constants that are fixed for our experiment. Sigma is a fundamental property of the ozone molecule called the absorption cross-section, and L is the length of the detection cell. Sigma, or the absorption cross-section, can be thought of as the effective area blocked by a single molecule of ozone. L is the length of the detection cell. For the GO3 ozone monitor, L is 14 centimeters, or about 5.5 inches long. Ln is the natural logarithm, the logarithm to the base e. I naught or I sub 0 is the light intensity when no ozone molecules are present in the detection cell. I is the light intensity when ozone molecules are present. Note that I naught is always larger than I, so the ratio of I naught to I is always greater than 1, so the logarithm will always be positive. After measuring I naught with no ozone in the detection cell and I with ozone present, we can plug the two measured values into the Beer-Lambert law and calculate the ozone concentration. So, in our instrument, we need a way to alternately measure I and I naught. This can be done by using an ozone scrubber to remove ozone and a solenoid valve to alternately switch the airflow between going through the ozone scrubber or bypassing it. The ozone scrubber is made of a material such as hopcalite that destroys the ozone molecules by converting them into ordinary oxygen molecules. A solenoid valve uses an electromagnet to repeatedly switch the flow path between a position where ozone passes through the ozone scrubber and a position where ozone bypasses the ozone scrubber. In 2B Tech ozone monitors, the valve switches every 2 seconds. Here we see air bypassing the scrubber. Some of the light is blocked by the ozone molecules, and the UV light intensity I is measured. Here the air passes through the ozone scrubber and no light is blocked, and we can now measure the UV light intensity I naught. From our measurements of I with ozone present and I naught with no ozone, we can now calculate the ozone concentration using the Beer-Lambert equation. We could calculate an updated ozone concentration each time we measure a new value of either I naught or I, which is every 2 seconds. However, most applications don't require such a fast response time. Let's take a moment to examine the units of our calculation. The concentration of ozone is expressed in molecules per centimeter cubed. The units result because the units of the absorption cross-section are centimeters squared per molecule, and the units of path length are centimeters. Notice that the measurement is based on a light intensity ratio. Thus, we can express light intensity in any units. We could use absolute units for light intensity such as lumens, but since the units cancel, we can simply use the electrical measurements of the current produced at the photodiode in amperes. Or we can measure the voltage resulting from that current passing through a resistor. In all cases, the units cancel. All that matters is that the light detector, in this case a photodiode, output a signal that is linearly proportional to light intensity. As we have seen, ozone monitors fundamentally measure ozone concentrations using units like molecules per centimeter cubed. What is measured is the number of molecules in a cubic centimeter of air. Atmospheric scientists prefer to express ozone levels in fractional units, such as parts per billion or ppb. We are all familiar with the fractional unit of percent. Like percent, the unit parts per billion is a fraction. Percent is parts per hundred. Parts per billion, or ppb, are 10 million times smaller than percent. To visualize what 1 ppb is, consider circling the Earth with golf balls. It would take 1 billion golf balls to surround the Earth at the equator. One golf ball then represents 1 part per billion, or 1 ppb, of the golf balls. Ozone monitors are capable of measuring ozone with a precision and accuracy of about 1 ppb. A level of 1 ppb of ozone means that there is 1 ozone molecule for every 1 billion air molecules. Since ppb is the fraction of air molecules that are ozone, to express ozone in ppb units, we need to know the concentration of air molecules. The concentration of air molecules is completely determined by the temperature and pressure. So, to convert our ozone measurement from concentration units of molecules per centimeter cubed to mixing ratio in ppb, we need to measure the temperature and pressure inside the detection cell. This is done by adding temperature and pressure sensors to the ozone monitor. We can calculate the concentration of air molecules inside the detection cell using the ideal gas law. Here, P is the pressure in atmospheres, N sub A is Avogadro's number, R is the gas constant, and T is the absolute temperature in Kelvin. Avogadro's number and the gas constant are accurately known constants. We only need to measure P in atmospheres and T in Kelvin to calculate the concentration of air molecules. If we measure T in Celsius, we can convert it to Kelvin by adding 273.15. Using the ozone concentration measured by the Beer-Lambert law and the concentration of air molecules measured from the ideal gas law, we can calculate parts per billion. ppb is the ratio of the ozone concentration to the total air molecule concentration multiplied by 1 billion, or 10 to the 9th power. For example, if the ozone concentration is measured by the ozone monitor to be 1.85 times 10 to the 12th molecules per centimeter cubed, and the air concentration is calculated from the measured temperature and pressure to be 2.46 times 10 to the 19th molecules per centimeter cubed, the ozone mixing ratio is calculated to be 75 ppb. Let's now combine the two equations, the Beer-Lambert law and the ideal gas law, to obtain a single equation for calculating ozone mixing ratio in ppb. This is the equation used in all modern ozone monitors to calculate ozone. Since the effects of temperature and pressure on air density are included, ozone monitors that use this equation are said to be temperature and pressure corrected.